Okay, so we can use the previous lemma to establish a stronger result, which we will state as a theorem. Let m and n be positive integers, such that m is less than n, and let B be a proper subset of the set A, such that B is not empty, that is, a non-empty proper subset of the set A, if there exists a bijection, which we will call F, from the set A into a finite subset of consecutive integers from 1 to n for n greater than or equal to 2, then there exists a bijection, which we will call G, from the non-empty proper subset B into a finite subset of consecutive integers from 1 to m for m at least 1, but strictly less than n. So proof. Consider the bijection, which once again we call F, from the set A into a finite subset of consecutive integers from 1 to n for n greater than or equal to 2. We choose an element A sub naught in the set A and form the non-empty proper subset which we denote A sub n minus 1, which is the set A without this element A sub naught. Then, by the previous lemma, there exists a bijection, which we'll call G, from this set, A sub n minus 1, into the terminating subset of positive integers, beginning with 1 and ending with n minus 1. Now, if the cardinality of this set is greater than 1, we can choose a second element A sub 1 that is in this set and form the non-empty proper subset which we'll call A sub n minus 2, which is A sub n minus 1 set minus the singleton containing the element A sub 1, which is the same as the set A, set minus the pair A sub naught and A sub 1. Then, once again, by the previous lemma, there exists a bijection, which we will call H, mapping the set A sub n minus 2 into a terminating subset of positive integers beginning with 1 and ending with n minus 2. We can continue this process a finite number of times until we form the non-empty proper subset A sub 1 of the set A, which contains a single element and for which there exists a bijection mapping this singleton set into the singleton containing the positive integer 1. And hence, for any non-empty proper subset, B of the set A, if there exists a bijection mapping the set A into a finite subset of consecutive positive integers from 1 to n for n greater than or equal to 2, then there exists a bijection which we call G, mapping the subset B into a finite subset of consecutive positive integers from 1 to m for m at least 1 but strictly less than n. Okay, so this theorem has an immediate corollary. Every subset of a finite set is finite. So proof. Suppose that the set A is finite with cardinality n greater than or equal to 2, let B be equal to A, then B is also finite with the same cardinality as the set A. Now let B be a proper subset of A that is non-empty then, as the set A is finite with cardinality n greater than or equal to 2, there exists a bijection which we'll call F from the set A into a finite subset of consecutive positive integers from 1 to n for n greater than or equal to 2. So by the previous theorem, there exists a bijection which we'll call G, mapping the set B into the finite subset of consecutive positive integers from 1 to m for m at least 1 but strictly less than n. Hence, the set B is finite with cardinality M. So now suppose that the set A has cardinality n less than or equal to 1. Then the set A is either a singleton or is empty. So every subset B of the set A is either the same singleton or is empty. If B is a singleton, then there exists a bijection mapping the singleton B into the singleton containing the positive integer 1. And if B is empty, then by convention, B is finite with cardinality 0. And therefore, in any case, if A is finite and B is a subset of A, then B is also finite. And so every subset of a finite set is finite. Okay, so this corollary itself has a corollary. Every arbitrary intersection of finite sets is finite. So proof that the set containing a sub I for I in some indexing set I, be an indexed family of finite sets then the arbitrary intersection of these sets is a subset of each set a sub I in the family, where each set is finite. So the arbitrary intersection is a subset of a finite set, and hence, by the previous corollary, finite intersection of finite sets is finite. Okay, so a set is finite if and only if there exists a bijection mapping that set into a terminating subset of positive integers, a finite subset of consecutive positive integers. And this is the definition. There are some slightly weaker conditions that will allow us to establish that a set is finite. And so we'll state that as a theorem. So let B be a non-empty set and let n be a positive integer. Then the following are equivalent. B is finite. This is equivalent to the condition that there exists a surjection mapping a finite subset of consecutive positive integers into, or rather onto, the set B. That is, every element in the set B is mapped onto by at least one of the elements in a finite subset of consecutive positive integers. And so the cardinality of B can be at most n. This is also equivalent to the condition that there exists an injection mapping the set B into a finite subset of consecutive positive integers. Now, as this map is a function, each element in the set is mapped into the finite subset of consecutive positive integers. And as this function is an injection, if an element in the set of consecutive positive integers from 1 to n is mapped onto, then it is mapped onto by a unique element in the set B. And so the cardinality of the set B can be at most n. Now, before we actually start the proof, I want to talk about the technique that we're going to use. We are going to prove a chain of implications, a closed loop. We're going to prove that the first statement implies the second, which in turn implies the third, which in turn implies the first. Now, this is a much more efficient way to prove the equivalence of these three statements than proving three separate biconditionals, which would in turn require proving 6 separate implications. So as 1 implies 2, 2 also implies 1 via 3. As 2 implies 3, 3 also implies 2 via 1. And as 3 implies 1, 1 also implies 3 via 2. And so the technique that we will use is proving a closed chain or loop of implications. So first, we'll prove that the first statement implies the second. So proof. Suppose that the set B is finite with cardinality n. Then, by definition, there exists a bijection, which we'll call F, mapping the set B into a finite subset of consecutive positive integers from 1 to n. And so the inverse function, which is a map from the finite subset of consecutive positive integers from 1 to n into the set B, exists and is also a bijection. And hence the function F inverse, which once again is a map from the finite subset of consecutive positive integers from 1 to n into the set B, is a surjection.